Cool, good morning. So to start with, the title's Demystifying Performance, but why am I even talking about performance? To start with, depending on what sort of workloads you're running, if you're running a web app or you have a lot of processing, a lot of maybe audio-visual processing stuff you want to do. We've all got limited time in our lives. We probably don't want stuff to take literally forever. And it's pretty awful for our customers as well. So what I want to do today is kind of give you some performance fundamentals that'll help you better reason about performance. I think what I'm hoping is it's going to help you kind of identify performance problems or opportunities as well in your line of work. I think it's really important to understand these concepts. I'll go into what I kind of see a lot in just a moment. A bit about myself. My name's Nick Sear. I'm not actually a big old cheat sheet. I am a person. I forgot to put my photo on the profile page. I'm a staff engineer at VGW. I enjoy cooking and making cocktails, and I despise baking due to my lack of any concept of precision, which I carry into my software engineering. First of all, I'd like to thank our sponsors, obviously without which none of this would be possible. So, what do I do at VGW? I really specialize in sort of database and distributed system side of things. I do a lot of work with spanning the organization with that kind of thing. I've been there for about 6 years, and a big chunk of what I do is interviews. So in the past few years, I've probably done about 50 to 100 interviews. A bit of a cheat, I guess, what we do in our interviews, a big part of it is system design. So we ask the interviewee to design a system, like a web application or something like that, fairly simple. For some reason, half the time, this is what happens. It sounds funny, right? But a lot of the time, when we're looking for a systems architecture, for some reason, these things pop up first. All I've asked is for a web application. I haven't even discussed, what sort of throughput or what sort of latency we need. I just want to play chess with my friend. So we wouldn't really need these sort of things. What I do next is I kind of ask, hey, okay, how are these systems going to help with performance? And I kind of get this silence. This is kind of strange to me. This is like if I asked you to design a car and you kind of just sketched in like a rear spoiler and a turbocharger. I'm like, cool. Those are parts that can make a car fast. But it's not exactly a car. So what we might think is, okay, fine, all right, we've got to really go and understand all the little nitty-gritty details. I'm sure many of you would have heard or heard of a lot of these sort of things. I've got to really go and learn how compilers optimize things. I've got to learn how the CPU works, all these, very fancy advanced data structures. But I wouldn't really call these fundamentals either. I'd probably just say they're a collection of techniques and things we've invented to solve specific problems. So no, unfortunately, no matter how many of these you memorize, it's not going to make for a quick system either. So my talk's pretty simple. I'm going to talk about 2.5 things. We're going to talk about what makes individual applications fast and what makes distributed systems fast. And then we're just going to go through a few case studies of those hot new technologies we were looking at earlier. So Jackie Stewart was a F1 driver, British F1 world champion actually, who came with a very astute statement about how he's so amazing. He said, you don't have to be an engineer to be a racing driver, but you do have to have mechanical sympathy. I actually stole this off Martin Thompson, who does a lot of work with financial exchanges in London, who stole this off Jackie Stewart. The way I interpret is you don't have to know how to build a CPU or you don't have to know every in and out, but you do need to care how the hardware that's carrying your workload does its thing. So what we're going to do is we're going to walk through my very useless, very fast program. It's fairly simple. We have two arrays. The first array is kind of just full of, it's an array of numbers, right? It's 1 to 1,000. It's the 1,000 size array. We're going to double each element and put it in a new array. Pretty useless. In the first version of my presentation, I had it so we just put the assembly up here and we'd walk through it. I've kind of wound that back a bit because I think that's assembly specifics aren't really the focus. Don't stress too much if you're not too familiar with things like low-level CPU stuff like registers and things like that. I will walk through everything. What you do need to point out, and I've kind of bolded it up here, maybe a little bit hard to see, is where we're moving data. You see, if you can imagine like a 4 int equals, 4 int I equals 0, I less than 1,000, I plus plus, blah, blah, blah. We're loading in the I between registers. We need to load our number. Our array's in memory, of course, so we need to go and load it from memory into our cache and registers. We double the number in that register and put in another register. That we take it out of that register we saved it in and put it back in main memory. And then we do our I++, and we keep on looping through the array. Register, 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 blah, blah, blah. Why do you care? So this is roughly how long it takes to do data access between the different places you can kind of store your data. So registers, very quick. It's 1 clock cycle. We've all got these 4 gigahertz amazing CPUs. So if you do a bit of quick math, and that's kind of less than a quarter of a nanosecond. Cache is a little bit slower. Memory's a fair bit slower. Disk is way slower. And network is, it's not brilliant. This will be a little bit easier to understand if I go and kind of magnify it by a factor of, I think, 4 billion or 40 billion. Anyway, 0.25 nanoseconds becomes a minute. So you can kind of think of, if you're reaching out to a register, that's kind of grabbing something from your fridge. Cache is a little bit further out. Main memories, you're kind of going to the next town, kind of like Albany or something, to go get what you need. If you're going out to disk, that's going to take a while. And network is way off. So you can kind of imagine, right? If your application's constantly reaching over the network to get the data you need, you're not going to be particularly fast. So going back to our example, what I'm going to focus on, register to register is super fast. Who cares about that? The interesting part to me is how we're going to load from main memory into our registers. So we're going to grab the first 16 numbers of our array. I'm treating these as 32-bit integers. Cache lines tend to be something around 64 bytes in length. That's the minimum chunk you can go and grab from main memory. If you try to grab a little bit of it, what you're going to do is you're going to grab the whole 64 bytes, you're going to pull out one integer, and you're going to throw the rest out, which isn't the most efficient thing to do. So our memory subsystem is going to go, all right, I've got to get the first number. I don't have this cache line in memory, and I need the first number from it. I'm going to go for a big stroll down to main memory. I'm going to go grab it, and I'm going to load it into level 3 cache. I just want to make it a little bit closer each time. As you use it more, as we iterate through our array, it's going to get promoted, from level 3 to level 2, and then eventually level 2 to level 1. Awesome. So this is great, right? Now, every time we need to iterate through the next element of our array, we're just going to that level 1 cache. We're getting that sort of nanosecond, sub-nanosecond access time. This is awesome. But we've only loaded in 1 cache line, right? What about when we hit, the 17th element, so number 16? Are we going to have to go run down to main memory again? We're not. Mysteriously, someone's gone and put the next cache line, or a couple of the next cache lines, including the numbers that we need to double, into cache. That's the data prefetcher. So that's a component of the cache subsystem that's going to go, hey, you're doing something pretty obvious. You are just grabbing cache lines from memory sequentially, right? It's just an array. I'm going to do you a solid, and I'm going to go and grab these from memory and just pull them in for you, since you're doing a very obvious type of memory access. That's very awesome. What does all of this mean in reality? The difference is pretty stark. This is a small benchmark, pretty quickly written. I just ran out on my laptop. If you think about what we said before, we know, I'll tell you that an addition's usually one cycle on most modern processors. So given, we've got a 4 gigahertz processor, I'm just saying, the fact that we end up in the billions of additions a second is not particularly surprising. And I really want to get away from this idea of, we need 1,000 nodes and millions of dollars in cloud spend to reach this kind of throughput. It can be done on your laptop if you're willing to, if you're taking care with your data access. So you'll notice as you kind of go into you're reaching from slower and slower data stores, the throughput absolutely goes down. It goes down from that fantastical billions number down to something we see more day to day. So when you're reaching out to disk, it's in the hundreds of thousands. I didn't test network. I'm guessing it's going to be in the tens of thousands. So I'm going to go and mess all this up because it's kind of fun to screw things up. Same program. We're doubling an array. But I'm going to mess with the data structure. Instead of an array of integers, I'm going to turn it into a hash map. Now, the values in the hash map are well, technically they're still a number, but it's a pointer to an integer object. This ruins everything. You can't do this anymore. What you're going to do instead is stroll through your hash map's values, and for every single element, you're going to have to go and find that derest in the pointer and go find that thing in memory. You're going to grab a single cache line per element. You're going to pull out your little number, and you're going to use that and throw the rest away. That horrible thing we said we were doing earlier. So we don't have nice sequential access anymore. It kind of looks like this. You load in a cache line, you put it into cache, you grab one element out, and you never use it again. You do this over and over and over again. As you see from the benchmark, there's no wonder it gets so much slower. And we've gone to ruin Doggy's day. Without predictable data access, the prefetcher doesn't really know what you want. You're just grabbing data from all over the place. It doesn't know what to grab next. I'm going to dump a whole bunch of stuff onto screen. Don't try to read it. You'll notice that I've kind of focused a lot on talking about the CPU. Sequential access, this kind of thing. The reason I explained it this way is because RAM and disk kind of work off the same concepts. In main memory, obviously, we talked about lines of data. On disk, you have the same same concept. You really grab data in blocks. The problem with random access is you keep loading in whatever the smallest smallest size of data you can get from a disk or from memory. You load that in and you're chucking out so much. On top of that, if you have unpredictable data access, the caches on your disk, the caches close to your CPU, they get loaded in and then they get chucked out. Whereas if it's sequential, you're constantly able to read from that thing you've just loaded in. And it's a really fundamental concept for caches. So how do we keep the CPU happy? 3 key things, I think. Spatial locality. So trying to grab, you do kind of need to know how your data looks in memory. And once you have a rough idea, you can kind of think of your program going through doing things sequentially. This is a good thing. Temporal locality. Similar concept, but across time. You go and write data. You want to read it out while it's still hot in cache. If you go and do a stuff, you go write the data and you go walk away and go do something else, and you come back, probably something's already overwritten it, you're going to have to load it back into cache again. So you're constantly having to pay this cost of going and striding all the way to main memory. Data latency and throughput is pretty stark. We saw how you went from register, cache, main memory, disk, network, and so on. Things just get slower. There's kind of two more concepts to kind of wrap up what I consider to be application performance. One crucial one is synchronization. This really factors in where you're doing a lot of concurrent workloads. So one thing you generally want to avoid is doing a lot of shared data access. And what I mean by that is specifically write and read access to the same chunks of data. To do that safely, we use something we call a lot of synchronization primitives, lock semaphores, latches, monitors, that kind of thing, which you might have heard of if you do a sort of high performance concurrency. We really want to avoid that. I'll dive into how we can do this later. It kind of falls under the concept of weight-free data structures. So things you can access without stepping on toes of other contexts. Because one thing that happens when you have to introduce these sort of primitives is it's like roadworks, right? You kind of all need to go single file to do it safely. If you kind of merge, two cars together, don't merge two cars together. It means a thread's like, oh crap, I got to wait for someone else. I'm going to go drop what I was doing and go do something else. I'm blocked. It's absolutely rubbish for performance. A lot of context switching, which is very expensive. The other side of things, and probably my first hot take, hopefully not of not too many, I think doing leak code or hacker rank will make you a better software engineer. If you haven't heard of those, they're kind of programming problems that will run you through implementing and different data structures and algorithms. One thing I really like about it is when you submit your solution, you kind of get that timing back. You know that 1,000 iterations of your solution took, 100 milliseconds, and you know kind of where you rank, who did it faster. It's really quite nice. Frankly, you're going to find it very difficult to write high-performance applications if you don't know your data structures, because you don't know what it looks like in memory and how it's accessed. And if you don't know your algorithms, you're going to do a lot of really wasteful work. You're going to do these, loop kind of things. These are things you can practice and learn. So, ending on the last two, I'm going to say, let's also avoid weights and synchronization, and we do care about algorithmic efficiency. I don't know if this will help, but we'll try explain from another angle. Access data in batches, access data predictably, beware of slow data access, try to avoid sharing data among multiple contexts, and be lazy. Why have your CPU do a lot of stuff if you can just not? And this actually bubbles all the way up. It's not just algorithmic efficiency. If you've got all these features and workloads that you don't actually need, aren't giving customers a lot of value, or aren't really useful, delete them. This is something I think we don't see enough. On one hand, we don't throw away stuff that isn't giving value anymore. And on the other hand, I think we don't spend enough effort on understanding the problems we're trying to solve, which leads to these overcomplicated things. I'm not going to go too much into it. There's a really nice talk that's coming up from Matt James later today about really understanding problems. But I will say, you cannot build a high-performance system without really understanding your problem. Just take a breather, because this is kind of the end of the application performance part. The presentation's going to get a lot cuter from here on, and then it's going to get less cute. I didn't spend enough time finding a clip art lion, so this is the one we get. Distributed systems. So, I guess, kind of way away from what we were talking about before, the fundamentals for performance in distributed systems are quite different. A distributed system is basically a set of nodes that are handling your workload. We don't need to do anything special to make these things fast. By default, they are very quick. If you don't have any reason to coordinate between nodes, you can just scale out your, you can just go and buy a bajillion instances of EC2 in AWS and just keep scaling pretty much linearly as you run your workload. So it's kind of like, just imagine just a whole bunch of lines and you're just throwing fish at them. They're going to eat it as quickly as you feed it to them. This is pretty common for workloads like media processing, so image, video, audio processing. Also a lot of mathematical workloads, like Monte Carlo simulations for, I think, for a lot of quant trading stuff, statistical analysis, protein folding as well. I think one of the key aspects of this is, you can just give this, you can give a line of fish, or you can give your system a piece of work, but you don't really care if it gets saved, right? If it fails, you just retry. You're just looking for pure throughput. That's not usually the case for a lot of our distributed systems. So what I'm going to do is I'm going to talk about ACID a bit. ACID's nice. It gives us all these nice guarantees. What rarely gets talked about is the cost. So at the moment, these lines are having absolute blast, and you just go eat fish. I want durability. All right, these lines now have to, go and run 10 meters, 100 meters, go and put their paw print on the on a piece of paper to say they've gone and eaten their fish, and then they get to eat their fish. But they need to do that run first, and a little bit sadder. Durability is expensive. We talked about the cost of reaching out to disk, reaching out to network before. You want durability, you're writing to disk. And you're just not writing to one disk. What if that one disk blows up? You want to write to a range, probably 2 or 3 nodes. So what are you going to do? You're going to wait for all 3 nodes to save the data, and then once those are done, you're like, okay, cool, that's done. Awesome. Now your latency is the worst of all of the write to all 3 disks. You can work around this. You can improve this a little bit with consensus, so you don't have to replicate across every node, but just a majority. Still, you're paying the cost of writing to disk. One thing you can do is, hey, let's just not wait. Let's just fire it off to disk, and that can write in the background. All right, cool. Now there's a delay between what you've written to the system and what's written on disk. So when your disks crash, you're going to lose some data. But at least you're not waiting as long. The latency is a little bit better. The most common, that's kind of the difference between synchronous and asynchronous replication. Synchronous is much more, you won't generally lose data with synchronous replication unless all your nodes fail. But you do pay that extra latency cost of waiting for the slowest node. Asynchronous replication kind of moves away from that a bit. You don't wait, but you can lose data. Cool, that's the D in ACID. Atomicity, that's a nice one. So I'm really stretching this analogy a bit. I'm going to say that we want all the lines to eat their fish, or not at all. So there's a very common method for doing this called a 2-phase commit. Let's walk through that. How are we going to get all the lines to make sure they all eat their fish? Give them their fish, but no touching yet. Now put it in your mouth. Okay, we screwed up. One of the lines is put on their head. Let's roll back. Let's prepare again. Okay, the lines have all got the fish in their mouth. We can commit. Now, this seems like a pretty absurd protocol, and that zookeeper we have there isn't just for show. That is a component in this system called a coordinator. If any of the parts of this system fail, that data is unavailable until at least the coordinator comes back up, or the majority of the nodes comes back up. This is absolutely absurd. I don't know why anyone would use this. Anyway, these guys use it. It's pretty pervasive. It's kind of crappy, but it's the best way we figured out how to do it. Cool. That sounds expensive. Consistency. Specifically, we want to be able to provide specific consistency guarantees. This means, for example, when I write to my system and I go and read from it again, I do see my write. Not every system guarantees that, right? There's kind of there's one common way of doing it and one uncommon way of doing it. The one on the right is partition consensus. That basically means when you go and shard out your system, you go and divide 100 pieces of data and you go split them up among different shards. Each shard kind of has their own consensus group. What you have then is you kind of need to ensure a order of writes, an order of transactions between those different consensus groups. And that requires some stretching. So one way to do it is with a single coordinator that kind of doles out, you get this ID, you get this ID. That's not great. We've just destroyed our availability and our throughput because we just have a single node to go through again. The other way of doing it is with what we call clocks, and they have their own problems. We basically try to say, we just want to, we look at the wall clock, we go, okay, this event happened this time. The problem with that is clocks it's very hard to get clocks synchronized between different nodes. So we have this amazing method of, what Google did was basically they bought a whole bunch of atomic clocks, they're kind of millisecond accuracy, and there's like, okay, these kind of drift apart by 2 or 3 milliseconds. We'll just wait out the uncertainty. So Google Spanner works with uncertainty nodes, uncertainty windows. You just wait until a clock shouldn't drift this much, and then you apply your next transaction. Whereas with single leader, kind of the original problem, you have a single leader that needs to coordinate on what's going to the system. A little bit of a really quick aside, a bit of a rant. We talk about strong and eventual consistency a lot, which is kind of like talking about second and sixth gear a lot. There are a lot of other different consistency guarantees you can make use of with different performance characteristics. If you understand your problem, you can make use of these a bit better. Cool. All right, what's this look like in the real world? I said I'd talk about those hot new technologies. Ooh, Apache Kafka. It's a high throughput replicated message stream. If I was on the Kafka marketing team, I could say so many more things. I won't. Kafka is probably the least interesting thing in the world. It's a replicated log. You can make your own log by doing you make a file and then you just echo to the file, and then you echo again and you just write to the file. I don't know, we've been doing this for 60 years. Oh, but we copied it across multiple computers. Now it's state of the art. This is actually the core of Kafka's performance. You do sequential reads and you do sequential writes. It's as fast a database as you can get. Better way you call it database. Another thing you can do is just batch messages together. So instead of sending one message down to disk at a time, you go and batch together 100, and then you go send it down to disk. So you don't have to do so many of those commands to send it down to disk, right? Cool. This really increases throughput. You're doing less work. And I've just flipped. It doesn't reduce latency at all. That's a terrible lie. I'm sorry. It increases latency because you're waiting for that batch to fill up. Another key technique it uses is called zero copy. I usually talk about trade-offs a lot. I don't think zero copy actually has much of a trade-off. I think it's just a nice thing to have. So pretty standard. We go and read from disk into a buffer. The application reads from the buffer, drops it back into into what we call a socket buffer, which the network card's going to read from and go funnel that over the network. You don't need to do that if you're using something like Java New I/O and your operating system supports it. You can just load into a buffer that the OS is going to kind of handle for you. It's going to map that buffer that's reading from disk to the one that's kind of bound to the network card, and it's going to do a straight copy, so your application doesn't need to handle it. It's pretty great. So when you want to use Kafka, it's a high throughput, durable, ordered message stream. Order's kind of with an asterisk. When you do partitioning, it's very difficult to maintain order across partitions. Anyway, don't use it as a database or for low latency workloads. It's not really designed for that. The idea of just finding a row in Kafka is kind of just scanning through it's a whole lot of big sequential scans. You don't want to do it. Redis, the rear spoiler of software engineering. What's special about it? it's pretty quick. It supports really high read and write throughput. How does it do that? Well, I think its default configuration, it just doesn't write to disk. We're just writing to memory. We have these really simple data structures as well. So we have this excellent sort of spatial and temporal locality. A more recent thing, it also makes use of, in its cluster configuration, it also makes use of something called conflict-free replicated data types. These are some pretty fancy data structures which let you sort of, for example, if you want to do like a distributed counter across a whole bunch of Redis nodes, there's an easy way to do that without stepping on each other's toes, which is to kind of have a big array. Each slot in the array kind of has the maximum value of each node, and then you just take the max value. So that's kind of alluding to that weight-free thing I was talking about a bit earlier. Don't share data access if you don't have to. What's the trade-off? Hopefully you can see that on the screen. It has pretty poor durability. So by default, if you're not writing to disk, the node crashes, you lose all your data. If you're treating it like a cache, you probably don't care. You may have some cold cache problems, for example, because while the Redis node's reloading your application, you just get smoked. You can also write to disk. They say, these companies say, oh yeah, we can write to disk. We offer durability, but that comes back to that asynchronous write and sort of synchronous write problem we talked about before. With the synchronous writes, which Redis you can ask Redis to do, it goes and writes all of the data you're putting into a log that it can use to rebuild itself if it crashes, but it does that asynchronously. It tells the client, yeah, all good, I got your data, while it hasn't even written to the disk yet, but it maintains its latency doing it that way. To make sure it can access this data quickly, it only really provides some really basic data structures. When do you use it? Probably the best use for cache, obviously, is read-heavy workloads that don't require linearizability, aka strong consistency. But let's keep calling it linearizability, because I don't know what strong consistency means. Next one. This one's hot at the moment. CockroachDB. Netflix uses it. Ooh. What's special about it? It's a high-throughput ACID database with conflict-free multi-master support. So for a bit of context, multi-master is very cool. It means you can have, a database in America and a database in Australia, and they can both take writes. A very common problem with that is like, okay, let's say you write to the same piece of data at the same time. You've got a conflict now. Which one takes precedence? We'll talk about that in a little bit. That absolutely silly technique we were talking about earlier, two-phase commit, that's how it lets you do atomic transactions across the different ranges of data. Consistency in ACID doesn't mean consistency in distributed systems. It means your stuff like unique constraints and foreign key constraints. I'm not going to go too much into how that works because it's not that interesting to me. Isolation ties closer to consistency in distributed systems, I guess. The way we did clocks I was talking about earlier, that's kind of how it achieves isolation. What it does is it goes and tries to order all of your transactions in a certain time period, plus that uncertainty window. And if transactions land during the uncertainty window, it goes and it just goes and retries. That's its way of separating the transactions from each other. CockroachDB didn't fork out for atomic clocks, so when they use hybrid logical clocks, the latency is a lot worse because they just use regular pleb clocks. And durability, you'll see this pattern repeated over and over again. Every data store that does durability just writes to a log. That is the fastest data structure. I don't know why you wouldn't. As I kind of talked about just now, how does it do that conflict-free thing? It goes and you have a serializability violation if kind of two transactions go and land on top of each other. So the one that lands later will kind of retry or fail depending on how you've configured Cockroach. This is kind of nice because you know that your data, you're not just going to drop data on the floor. This is in contrast with DynamoDB, which does last write wins, which means whichever transaction wins later just overwrites the previous one. Cockroach is waiting for your, for your transactions to kind of spread themselves out, so it's got worse latency. Dynamo has has lower latency for writes and better availability because it's just steamrolling whatever came before it. The one that is probably far less in Australia, because we don't do a ton of financial exchange stuff, is a messaging transport called Aeron. This is used at quite a few financial exchanges in London. It was developed by Martin Thompson's team, the mechanical sympathy guy from before. Mechanical sympathy is also the name of his blog. I put a little graph up here to see, to show it's smoking everything else. Don't worry about the details, it's just super low latency and so super amazing. So what it is a ultra low latency messaging system used by trading platforms. There's another lie, it's not durable at all, I'm sorry. So the way it kind of works is pretty simple. It takes a publish, subscribe, a pub/sub model, right? You go and write you go and publish, you go and save your command into a ring buffer, well, I'll explain in a bit, and you go and save the contents of your message into a log. I feel like I've said log way too much today, but anyway, it does write into a log, very fast sequential writes. Sorry, tired of hearing that. The ring buffer side, we talked before about not wanting to, share data. We want to be very selfish. A ring buffer is basically a fixed length array, so you don't need to spend time, grow. You can't grow or shrink it. Instead, you have these two pointers which point to the head and the tail of the buffer. With a bit of modular arithmetic, you can kind of just you can have your publisher publish to this side of the array and consumers reading, following it, but they never quite step on each other. Of course, it's fixed length, so you can run out of space there. That kind of acts as a natural sort of back pressure. So when the ring buffer runs out of the array, you can't publish anymore. What's the magic sauce? We talked earlier about messing up our process by swapping an array for a hash map. Aeron just implemented a primitive hash maps in Java that support primitive keys and primitive values, so we don't need to do that jump anymore. We talked about ring buffers, but I forgot to mention what we want to do. Aeron runs in the JVM. We don't want to have these great garbage collector pauses when we keep going and instantiating objects during runtime and using up all the memory, blah. Instead, we try to put as much of our structures in place when we boot up our application. We call this pre-allocation. This means that the application runs at more or less steady state. What that means is you're not constantly allocating more memory during runtime, so your garbage collector doesn't have much to do. That's pretty nice. Now we can kind of avoid these nasty hitches during the running of our application. This is important, especially for high-frequency trading. Microseconds matter. So a 100 millisecond garbage collector pause where your trade just stalls, that's a lot of money on the table. We talked about the log buffers. We've got excellent locality there. We've gone through zero copy before. They have an efficient way of encoding messages or encoding commands. What that means, that these are structures that are optimized for Aeron's workload, and they're a bit more compact, so we're sending less stuff over the network that we don't have to. I'm not going to talk about spin weight. So when to use Aeron? When you really need the lowest latency you can get. And this comes at a pretty significant cost. The biggest one probably being durability, which means that, hey, the message you've sent can kind of disappear at any time. You now go and need to handle that somewhere else, probably in your application. There are plugins like Aeron Archive, but that will write to disk for you. But you can't get away from these ironclad rules. Durability versus latency is an ironclad trade-off. There are no magic ways you can get around this. You do synchronous writes, it's slower, but you'll minimize data loss. Asynchronous writes, you'll lose some data, or you don't write to disk. It's obviously the fastest. That's it. There's no company on the planet that can engineer their ways around that. All of these systems are built on those same fundamental rules. Aeron shifts a lot of that the complexity to get that low latency over to your application, and much like Redis, it provides a relatively minimal feature set. I'm probably being a bit unfair to Redis there, but it's fine. The key here, I've tried to sort of whittle this down as much as I can. The way I found easiest to reason about application performance is to think about how you access data. Because the CPU by itself, if it doesn't really need to do much data access, is staggeringly fast. It's fast by default. We do things that make it slow. In a distributed system, I think the major cost, same thing. To begin with, like workloads on distributed systems are what we call embarrassingly parallel, which means you can just add more nodes and it just gets faster. It's when you go and add these constraints, durability, atomicity, consistency, ordering, these sort of things, that you really start to slow down your system. And the key then, I think, to making a high-performance system, again, you need to understand your problem. What am I trying to solve? What guarantees do I actually need? Because every single one of those guarantees is extremely expensive. The last one, which is a little bit unrelated, I think a mistake we can make is kind of walk away from this and be like, oh, okay, I know I kind of have more sense of how to reason about performance now. I'm just going to do this change and that change. You need to measure. Measuring's difficult, and I'm kind of doing you dirty here by not explaining how to do good benchmarks, but that's really its own big topic. But there's plenty of great resources on the internet about it. You do need to measure the performance of your system if you're building these things, because the results can be very surprising. Things can be counterintuitive, and there's a lot to be learned there. Thank you very much.
Do we have any questions for Nick? We have 1 minute, so you could probably take one question. Any questions? I'll go with this one.
Hey, thank you for that. I think that was one of the most beautiful slides with this cute tiger and lion and stuff. My question is not related to more technical stuff, but I work as an engineering manager. I think a lot of this is very relevant to us. Deval here, my friend, we work together at ClickSend, and a lot relevant. You, at the beginning, mentioned that you spend a lot of your time doing interviews. So it kind of caught up my mind where a lot of these things are really important for business, especially for us like ClickSend. We send millions and millions of messages. How do you grow that as a staff engineer to the other people or the junior engineers? Does it seem more relevant, or how do you plan for getting these kind of things, grown within the engineering teams?
Thanks. That's a really interesting question to me. So, frankly, that is exactly what I'm trying to figure out at the moment. How to kind of, because across organizations, you've got kind of junior to senior and whatever. You don't want to go and deluge newer engineers in all of this detail, right? So I'll be honest, I don't really have an answer for you because I'm still trying to figure this out myself. What I think I'd like to start with is a talk like this. This is one I wanted to do internally. There's another one I referenced before. Matt James's talk in a few hours around understanding problems is also foundational, and I think great for junior engineers as well. What I'm going to do next is probably look at how to measure things. So benchmarking, it may not be the right next step, but it's the one I'm going to take. I'm sorry I don't have a better answer for you, man. I'm still figuring it out. Let's do it.
Awesome. Thank you so much, Nick, for the awesome chat. If you have any other questions for Nick, unfortunately, we've run out of time. Please feel free to reach out to him and on his LinkedIn as well.